So, welcome everyone to today's ISSI-BJ online seminar on the Solar Wind Magnetosphere Ionosphere Link Explorer CAS SMILE Mission. The seminar will be given by Professor Wang Chi, who is the Director General of the National Space Science Center of the Chinese Academy of Sciences, whom I would like to thank for accepting our invitation. And today's seminar is actually not the first one, but the third one in the context of the ISSI-BJ online seminar series called On Things to Come, which focuses on ongoing and future space missions, and which was started last September thanks to the work and efforts of the ISSI-BJ Executive Director, Professor Wing Ip, that you can see right now in the webcam with Professor Wang Chi. And I'm Laura Baldis. I'm the PR and editorial manager of ISSI-BJ. And before I give the floor to Professor Ip and Professor Wang, I would like to give you a very short introduction to ISSI-BJ and to our activities. So, ISSI-BJ was established in 2013. It's a research institute for advanced space science studies, and it was founded in 2013 thanks to the efforts and the cooperation between the International Space Science Institute in Bern, Switzerland, and the National Space Science Center of the Chinese Academy of Sciences. And since then, since 2013, we've had thousands of scientists, engineers, researchers carrying out their studies here at our premises in Beijing, of course, and organizing several activities ranging from forums to workshops, working groups, international teams. We've had visiting scientists and covering several actual research areas in space sciences. We've had, unfortunately, this year no in-person face-to-face meetings due to the current situation, to the pandemic, but we all hope that the situation will improve very, very soon, and therefore that next year we will be able to have in-person meetings at least as soon as reasonably possible. So before further ado, I would like to give the floor to Professor Ip, and thank you everyone once again for being here.
Yes, Lola, thank you. It's my great pleasure to introduce Professor Chi Wang today to give the talk on this very interesting cooperative project between China and ESA. I just want to tell you that Professor Chi Wang, he finished his undergraduate study in China at the University of Science and Technology of China. And then he went to America for his graduate study. So he obtained his PhD degree from MIT in 1998. And a couple of years later, he returned to China and to work at the National Space Science Center. Currently, he is the Director General of the center. And his research expertise is on solar wind and space plasma physics. Currently, he's the mission co-PI of this SMILE project. The name, I think he will tell you, the long name is called the Solar Wind Magnetosphere Ionosphere Link Explorer. And he is also the Deputy Chief Designer of the Chang'e 4 Lunar Exploration Mission. And I'm sure that in future, he will come to tell us more about China's space program. But for now, Professor Wang, please start your lecture. Thank you.
Okay, thank you very much, Ip. I will show my PowerPoint.
It's the button on the left.
Is it okay?
No, not yet.
No?
I can't.
Not yet, okay.
Professor Ip, can you see his screen?
Yes, I can. Yeah, okay. Here's this first page.
Okay, perfect.
I think you could start now.
Okay. Good day, ladies and gentlemen. Dear colleagues, first I would like to thank ISSI-BJ for inviting me to give the talk in the new online seminar series on things to come. I'm glad to have this opportunity to present you the future mission SMILE, SolarWind Magnetosphere Ionosphere Link Explorer during this difficult time. SMILE mission is a new mission to image the magnetosphere in a global view. My talk will include 5 parts. First, I will give you some background, and then I will talk about the scientific objectives and the science payload onboard SMILE satellite. Finally, I will present you the mission profile and the current status. SMILE is a joint mission between the European Space Agency, ESA, and the Chinese Academy of Sciences, CAS, follows a successful collaboration of the cluster and the double star. Following the recommendation of the Joint Scientific Evaluation Panel, SMILE was selected by SPC Science Program Committee in November 2015. It is the first time that ESA and China joint select, design, implement, launch, and operate a space mission. The SMILE mission was adopted by CAS in November 2016 and by ESA in March 2019. The mission PDR was successfully conducted in January this year. It is expected to launch SMILE in November 2024 up to mid-2025 with 6 months of system level margin. As our world becomes even more dependent on complex technology, both in space and on the ground, society becomes more exposed to the effect of space weather. The interaction between the solar wind and magnetosphere and the geospace dynamic that result comprise a fundamental driver of space weather. The solar wind magnetosphere interaction is one of the key links in the Sun-Earth connection. The most important mechanism of the entry into, storage within, and released from the magnetosphere of solar wind mass, energy, and momentum is magnetic reconnection. The daylight reconnection is the main mechanism for particle and the energy of the solar wind enter into the geospace. The tail reconnection will release energy, injecting particles deep into the magnetosphere, causing aurora substorms. When the solar wind magnetic field points southward, magnetic reconnection and the magnetopause opens close the dayside magnetic field lines, causing the region of the open field lines in the polar cap to expand to low latitude. The amount of open flux depends on the rate of reconnection both on the dayside magnetopause and in the light side magnetotail. The polar cap is the area of magnetic field that are open to the solar wind and is readily identified by the aurora oval which bounds it. The open closed line boundary we call the OCP define the aurora oval. In fact, the open magnetic flux governs the substorm intensity. As you know, the magnetic field has been explored in situ by natural history of satellite missions for more than 60 years. What do we know about the magnetosphere? We have already known the basic features of the magnetosphere. For example, the position of the magnetopause. Magnetopause is the interface between the solar wind and the Earth, and this plot shows a magnetopause collision observed by an in situ satellite. A relatively sharp transition from dense shocked solar wind plasma to Tanning's magnetospheric plasma marks the magnetopause. In this plot, the magnetopause is indicated by a sharp jump in magnetic field BJ, number density, and velocity. Through thousands of crossing events, we can obtain the shape of the magnetopause and established a periodic model of the magnetopause. In similar way, we have already known the configuration of the magnetosphere. The interaction of the solar wind with the Earth, resulting in large structures of the magnetosphere, such as cusp regions, magnetotail, plasmasphere, boundary layers. And this plot shows the cusp entering observed by an in situ satellite. These yellow lines bound the cusp region. And this figure shows the statistic study of the cusp plasma during planting of cloisons. In addition to the basic features and the configuration of the magnetosphere, we also know the dynamic of the magnetosphere, including the magnetic reconnection, instabilities, and the response to the solar wind disturbance. And this plot shows a single closing of observation of the magnetic reflection. By reasonable assumptions, the real topology of the field lines near the magnetic structure, such as the regions of flux knob, could be reconstructed, allowing a tracking of the motion of these structures relatively to the spacecraft or constellation. And this figure just shows a reconstruction for flux transfer event, FTE, and the magnetopause. And this table just summarizes the dynamics of the interaction of the solar wind with the magnetosphere. For example, the timescale of the bursts of magnetopause reflection is about 1 minute or less, and the typical time between bursts, that is FTE recurrence, is about 8 minutes. The substorm growth phase lasts about 13 to 16 minutes, and the storm duration is about 1 to 2 days. So in the dynamics of the interaction of the solar wind with the magnetosphere, we have different time scales. Most of this important information comes from the in situ satellite missions. For example, I mentioned the cluster and the double star missions. And we also have 4 satellite constellation missions like MMS, and also 5 satellite constellation mission SIMMERS. So in situ measurement provide and localize the information about plasma field and their dynamics. However, they fail to provide the global view, large-scale configurations, and the overall evolution of the magnetosphere. It is fundamentally impossible to determine the global behavior of a complex system with sparse in situ measurements, even with the support of increasingly complex global computer models of the solar wind magnetosphere interaction. It has been recently discovered the outer magnetospheric boundaries can be imaged while the process of the solar wind charge exchange, X-ray emission. The solar wind charge exchange occurs when the highly ionized species in the solar wind, for example, the oxygen 7+, interact with the neutral atoms, for example, the hydrogen from Earth. An electron from the neutral is transferred to the air, initially in a highly excited state. On relaxing to the ground state, one or all photons are emitted, usually in the extremely ultraviolet or the softer X-ray. The energy band between 0.5 to 2 kilowatt is dominated by a few strong lines due to charge exchange by oxygen 7 plus oxygen 8 plus. The interaction of the solar wind ions with neutral atoms in Earth's exosphere produced the softer X-ray lines, with intensities that peak in the Casper and the magnetosheath. Solar wind charge exchange then be used to imagine the sharp density boundaries of the ball shock, magnetopause, and the Caspers. So here comes the SMILE. By taking advantage of the solar wind charge exchange X-ray emissions, SMILE will adopt a higher inclined and high aperture up to 20 Earth radial elliptic orbit to imagine the global magnetosphere. So what are the science objectives of SMILE? The first objective, of course, is to provide global view of the magnetosphere. Since the innovative prediction of the magnetosphere in 1940s, scientists have been studying this field for more than 17 years. With SMILE, we would actually see the magnetosphere for the first time and further understand its global features. Then, we need to understand the fundamental modes of the day-side interaction of the solar wind with the magnetosphere. SMILE will adjust when and where transition and steady magnetopause reflection dominate. Determine how solar wind parameters such as interplanetary magnetic field clock angle and the Mach numbers control the magnetic reflection. Quantitatively estimate of the energy of the entry of the energy of the mass into the Earth's magnetosphere from the solar wind. Through SMILE, we can improve our understanding of the substorm to define the substorm cycle, including timing and the flux transfer amplitudes, and to determine how open flux control the sequence of the substorm process, among others. Finally, to determine how CME-driven storms arise and develop, we need to investigate if there is any relation between the ring currents, partial ring currents, and the magnetopause location during the geomagnetic storms. To define the development of CME-driven storms, including whether there are sequence of substorms, and to determine if the solar wind density, pressure, or interplanetary magnetic field affect the storm and how. To summarize, SMILE is a lower mission that addresses basic micro-scale interaction questions about the solar wind magnetosphere coupling while simultaneously in situ solar wind magnetosphere plasma and magnetic field measurement, X-ray images of the magnetosheath and magnetic clusters, and the UV aurora images of the global aurora disturbance. In short, SMILE will investigate the dynamic response of the Earth's magnetosphere to the solar wind impact in a unique and global manner. Then I will talk about the science payload. In order to achieve the scientific objectives, the SMILE mission comprised 4 payloads. To address the question about the structures of the magnetosphere and the interaction modes, which require the information about the property of the solar wind and the magnetosheath. We then need a plasma particle detector, we call LEO, the low ionized ion analyzer, and the magnetic field measurements, MAC. It also required the information of the shape and the motion of the magnetosphere and the cluster, which will be given by soft X-ray imager SXI. The consequence of the magnetic recollection required the movement information of the aurora, which will be provided by the UVI. Similarly, the other 2 science objectives could also require the information provided by these 4 payloads. SMILE will deliver data of images, including the soft X-ray images of the magnetosphere and the clusters, to give the information about the large-scale structures such as ball shock, magnetopause, and the clusters, and the UV images of the aurora over, investigate the location and the structure of the aurora, and the in situ measurement, including the interplanetary magnetosheath magnetic field and the solar wind magnetosheath plasma information. Then I will give some more details about the payload. The soft X-ray imager SXI will observe the location, shape, and the motion of the dayside magnetospheric boundaries. The PI of the soft X-ray imager is Stephen Sabre from the University of Leicester, UK. The energy band of soft X-ray imager is from 2.2 to 5 keV, and the baseline is 2.5 keV, and the 5 keV is the goal. And the optical field of line is about 27 degrees times 60 degrees. The time resolution is about 1 minute, and the angular resolution is 6 arcminutes. The spatial resolution should be sufficient to track boundary motion, which is about 0.2 Earth radian. The fastest measurement cadence is required during the most disturbed times, about 1 minute. But to characterize the substorm cycle, a 5 minutes cadence is sufficient. The ultraviolet aurora imager, UVI, will observe the size of the polar cap, the location, and the width of the aurora over, and the transition and the localized brightness that occurring within and on the edge of the aurora over. The PI of UVI is Eric Donovan from University of Calgary and from Canada. And the wavelength band ranges from 114 to 118 nanometers. A 100 kilometers resolution imager with a 10-degree FOV and 20 Rayleigh sensitivity is required. The time cadence of the images should also match those of the soft X-ray imager. SMILE is a standalone mission, and which makes its own solar wind plasma and magnetic field measurement. Night eye analyzer NEO will measure the basic moment and the distribution function of the ions. The PI of NEO is Dailei from China. The energy range is from 14 eV to 20 keV. Field of view is 360 degrees in azimuthal direction and 14 degrees in evaluation direction. The relative energy resolution is less than 10%, and the time resolution is about 2 seconds. The magnetometer will measure the magnetic field simultaneously with the NEO. The PI of the mag is Rayleigh from NSC, and this resolution is 24 bits with noise less than 0.1 nanotesla. The sampling rate is 14 Hz. Two sensors are separated about 1 meter, and the outboard sensor is 3 meters from the spacecraft body. And this table summarizes the mass and the power for each payload. The total mass of the payload is about 64 kilograms, and the total power is about 111 watts. And the SMILE is a small satellite. So what do the SMILE data products looks like? Based on the global MHD simulation of Sun-Earth connection and the solar wind charge exchange with geospace neutral hydrogen resulting soft X emission theory. The left figure shows the soft X-ray imager expected data and UVI expected imager of aurora is similar to those UVI imager obtained from previous polar missions. The MAC and the NEO expected data are also the same as those in situ measurement from the solar wind and the magnetospheric space missions, such as the cluster and the double star missions. We use a solar wind storm on March 17, 2005 to simulate the response of the Earth's magnetosphere and its element to the income ICME, interplanetary coronal mass ejections. The left panel shows the time variation of the solar wind parameters and the DST index. From the top to the bottom panels, the parameters are the interplanetary magnetic field, plasma velocity, number density, and the temperature. And the bottom panel is the DST. And the right panel just presents the simulated X-ray imager. Of the shock arrival, a substantial increase of X-ray imagery is observed, as well as the compression of the magnetosphere due to the increase of pressure of the magnetopause. After turning of the IMF from northward to southward, the magnetopause is also observed to move inward, most likely due to the erosion of the dayside magnetosphere by magnetic reconnections. This is what we expected from the SMILE mission. In the meantime, the aurora mimicked by the ionospheric potential, field-aligned currents, and the ionospheric conductance also shows the intensity enhancement and the movement from the high latitude to the low latitude accordingly. And this just shows a vivid example of what SMILE satellite could observe during the solar storms. Finally, I will give a a short introduction to the mission profile and the current status. As I has already mentioned, SMILE Mission is an international collaboration project of space science exploration joined led by ESA and CAS. It is a new milestone of comprehensive and deep cooperation among scientists, engineers, and managers from both parties. For the spacecraft, CAS is responsible for the platform, including a service module and a propulsion module, and ESA is responsible for the payload module. As I mentioned above, CAS is leading the development of LEO and MAC, while ESA is leading the development of SXI and UVI. The spacecraft level integration, verification, and test will be conducted in China and ASTEC. Launch vehicle is under ESA's responsibility. The options including dual launch by Soyuz or Ariane 62, or a single launch by Vega C into the initial orbit from Kourou. The design baseline right now is a Vega C launcher. ESA is responsible for the launch site and the launch service, and will also provide the ground segment support. After spending some days or a few months, depending on the launch approach, in a low Earth parking orbit, SMILE will be ejected by propulsion module into a higher elliptic high inclination orbit with a period of about 14 hours. China Satellite Launch and Tracking Control Center, CLTC, will be responsible for the TC and TM of satellite. ESA will also provide ground station support. CAS will be responsible for the planning, commanding of the SMILE spacecraft with support from the ESA side. Both parties will cooperate to make science short, mid, and long-term observational plan, monitor the execution of the plan, analyze the performance of the payload in orbit, implement the collaboration of the payload, produce the quick look data and the science data product. The satellite orbit is a big inclination and highly elliptic orbit with an aperture about 19 Earth radius, and the perigee altitude is about 500 kilometers. The lifetime of SMILE is expected to be 3 years with possible 5-year extension. For each orbit, above 50,000 kilometers, all instrument is on, unless some avoidance angles are met. SMILE enters the full science model. Below 15,000 kilometers, soft X-ray imager cannot observed due to the CCT sensitivity to radiation. When UVI cannot observed due to the illumination constraint, SMILE enters into reduced science model with MAG, NEO, and soft X-ray on, typically between 32 to 5,000 kilometers. SXI cannot observe. SMILE enters into the reduced science mode 2 with MAG, NEO, and UVI on. Below 32,000 kilometers, except during the X-band communication, SMILE entered reduced science mode 3 with only MAG and NEO on. With close to Earth, the SMILE enters into the X-band communications mode for about 10 minutes. X-band transmission will meet CCSDS standard. The data rate is about 65 megabits per second. Data volume is about 35 gigabits per orbit. All above science operation plans are based on the SMILE orbit simulation to analyze the spatial relation among the Sun, Earth, and the SMILE satellite. The joint mission PDR was completely successfully in January in Europe, and which was the third joint review of the SMILE mission. And this marked the kick-off of the Phase C of SMILE satellite. Next milestone will be the mission CTR, which is scheduled in August 2022. Due to the impact of the actual export control issue, this is a ITA issue, as well as the coronavirus events. The launch date is delayed, which right now is expected to be the November 2024, 1 year later than originally planned. Of course, the new schedule is waiting for approval by the ESA SPC in later November this year and by CAS. In summary, SMILE will break completely new ground in the way we explore how the Earth's environment responds to activities on the Sun and in the solar wind, and will open the way to future systematic and large-scale monitoring based on state-of-the-art X-ray detection and mapping techniques applied to the terrestrial space plasma science. The cooperation of European countries with China, from mission to design to launch and fly the operations, I think is the large first of the SMILE mission. And the visit make it brilliant showcase, building on and extending the successful experience of collaboration between cluster and double star. Okay, I think I will stop here. Thank you very much for your attention.
Thank you very much.
Yeah, thank you so much, Professor Wang. So can you turn your picture on so that we can see you? Yes, thank you. So Lola, do we have questions to Professor Wang?
Yes, I sent the first two questions. And for all the participants, if you have any questions, you can use the chat box to submit them. Professor Wang, can you see the first two questions?
Yes, I see the first question is about the data policy. Yeah, the questions, will the data be shared with the international community? The short answer is yes. For some of the data of the payload, we will open to the international community immediately if the PI of the payload requests. Otherwise, all the data will be open to public after 1 year time period. The second questions, can you also observe the substorm activities on the magnetotail side? I think this answer to these questions is yes, because we observed polar aurora to define the substorm activities. But actually, we don't observe the in situ substorm activities in the magnetotail. But we can understand the substorm activity from the polar images. So I think this is mostly due to the activities in the magnetotail side.
We've received actually another question, but Professor Fabio Favata from ESA would like to thank you and thank the CAS colleagues for the great cooperation. Just a comment.
We also thank you, ESA, for this wonderful collaboration based on the mutual trust.
Perfect. And if there are any other questions, or Professor Ip, let's see. No questions at the moment.
Actually, I want to have asked a question that, seems that the X-ray, your soft X-ray instrument and the UVI would not be operating at the same time, isn't it?
No, for the full science mode, they will be operated. Most of the time, they will be operating at the same time.
Far away, from the
yeah.
So you have reduced
and also,
mode.
And also we can use the aurora observations from the ground observations. So for the reduce the science mode. So
And
we can establish the relation between the soft X-ray imager and the UVI aurora imager.
In one place, you mentioned about a double launch or separate launches, which I may have heard it incorrectly. But this is only one single spacecraft, right?
Yes, but probably for the Arena 62, this is a very large launcher. SMILE probably just one passenger. So with the piggyback launch.
Okay. That's what you mean by double launch. There's a two space.
Yeah, exactly. Yeah.
I think Professor Bonnet might have a question, but he raised his hand. But I haven't received the question yet. Also, unfortunately for all participants, unfortunately I can't turn on your audio, but if there is any question, always in the chat box. Let's see. Okay, we have another question. Here it is. What will be the time resolution for Aurora images? By Professor Alexei Dmitriev.
About 100 kilometers.
Okay.
For this is time resolution, is similar to the SXI from the probably from the 1 minute to 5 minutes.
Okay. If there is any other question.
I will also want to ask, because your instrument, your mission basically is for remote sensing, for X-ray, soft X-ray, and UV imaging, and so it will be very useful if you could. So if the SMILE data observation could be coordinated with other missions, other in-situ measurements. Is there such a plan?
Yes, very good questions. Actually, we will cooperate with other in-situ observations. For example, like the MMS missions. So we can compare the image missions with the in-situ measurement missions.
Right.
I see no other question coming in at the moment. No. I think Professor Ip, if there is no other question, and if you have no other comment.
Yeah, I think we could tell the audience. In fact, this video will be recorded, right? Be posted on the ISSI-BJ website, so people could always go back and take a look. And if they have questions, I'm sure that Professor Wang will be very happy, and his colleagues will be very happy to answer. So this would be a kind of continuing process. And
if you have any more questions, just send me an email.
Perfect. I received actually also a commentary by Professor Roger Bonnet, who congratulates you on the excellent presentation and the presentation of a highly important mission that is setting up a unique example of international cooperation.
Thank you, Brian. What a surprise.
Okay, but no other question. So again, if there is no other question, I'm displaying here the lineup of our upcoming seminars. And I would like to thank you once again, Professor Wang Chi, for his excellent presentation.
Thank you very much.
Thank you very much.
Okay. Thank you once again, and thank you everyone for listening.
Yeah. Bye-bye.
Bye-bye.
Bye-bye.